Alright, so today we're just going to delve into the basic ideas of forces. To begin, I believe that many of us probably know the basic equation, as you can see highlighted in the white. Force equals mass times acceleration. So for example, if you had a basketball that weighed a kilogram and you started pushing it at a rate at which it accelerates at 3 meters per second squared, then 3 meters per second squared times 1 kilogram would ultimately give you 1 Newton, or kilogram meter per second squared. Let me just write that out. Kilogram meters per second squared. So that's the unit. Oh, let me redo that. That's the unit for how we're going to measure forces. And the shorter way to say that is, once again, just Newton. So if you want a textbook definition of forces, I think it's the easiest to simply use the equation. So it is an acceleration of a mass. And to visualize these forces, I want to go into some basic vocabulary for the types of forces that we have. So first, we have the gravitational force, which is essentially just like the gravitational force upon anything within a gravitational field. So for example, the gravitational force is technically acting upon us right now because the core of the Earth generates a gravitational field which pulls upon us, and that pulls us downward towards the core of the Earth. We're accelerating. And if we didn't have the floor beneath us, then we would accelerate down towards the core at a rate of 9.8 meters per second squared. So as previously mentioned, I mentioned the floor. And that's important because that links right into the next term, which is the normal force. And the normal force is essentially just defined as the force that the floor or the ground exerts against an object. Because every object technically has weight, so for example, we have weight, because the gravitational force is pulling us to the ground, the normal force must counteract that by pushing up against us. So gravity pulls us down, and the floor pushes up. And that's why we stay still, and we don't float up, and we don't go down. Some other basic forces are the tension force, which is just basically a simple way, or a more complex way of saying a force that is exerted by a rope. So for example, if you have a chain that is attached to a tire, the chain is exerting a tension force because it is tied to the tire and is resisting the force of gravity. And then finally, we also have the applied force, which you could label anything as an applied force. You can even label ropes with applied forces, but you could just think of it as a push or a pull. So anything besides gravitational or normal can generally be labeled as an applied force. So now that we know these vocabulary terms, I'm going to go into a demonstration to help us visualize this. So for example, if we have a basketball that's just sitting on the ground, let me draw that in a better location. A basketball just sitting on the ground, and we want to draw a free body diagram for this basketball, which is essentially just a representation of all the forces that act upon it. First, I like to start out with the gravitational force because it's one of the easiest. So you just draw an arrow pointing straight to the ground because once again, or for the first time, forces are vector quantities, so they indicate direction. So this arrow indicates that the gravitational force is pointing downwards. So gravity pulls it down once again. So you have the gravitational force. But if the basketball is just sitting still on the ground, there must be something to counteract that. And that force is the normal force. So this is the force that the floor exerts pushing up on the basketball. Alright, so now this is just a basic basketball that's sitting on the ground. But let's make it a little bit more complex to demonstrate the other forces. Let's say I tied a rope to this basketball at its side and started pulling it to its right. I would demonstrate that by drawing this arrow as a representation of the rope pulling on the basketball and labeling it FT. And then finally, let's say, or before that, if this basketball were just represented like this, that means that it's an unbalanced force. So So if we were to visualize that, we would essentially just see a rope pulling the basketball towards the right as it accelerates. So the ball is accelerating as the rope pulls it. It's unbalanced because essentially it's accelerating towards a particular direction. So that means that the forces are not balancing out. So there's an unevenness to this. However, we need to be careful with how we label it as unbalanced because it's only unbalanced horizontally. But if we look at the vertical directions, the gravitational force cancels out with the normal force, so essentially it's balanced in terms of that. But because there's a tension force with nothing else to counteract it, it's accelerating towards a particular direction. But now if we were to balance it, for example, if someone were to push against the force of the rope with an applied force to the left, then what we would see is that the ball would stop accelerating to the right. And when I say that something becomes balanced, it's important to know that when I say that when something is balanced or it is at equilibrium, essentially what that means is that it is not accelerating in any particular direction. So if something is still, it's balanced because it's accelerating, or it's not accelerating at all. Its velocity is 0 meters per second. But if you have a car moving at constant speed, so its speed doesn't deviate at all, then it's also technically at equilibrium because it's not accelerating in any particular direction. That'll be useful for the future. But now let's go into the specifics of the problem we see right here. So essentially what we see with this problem is it says 2 snowcats in Antarctica are towing a house unit. The sum of the forces, so the forces we see are force A. Oops, let me get a better color. We see force A right here. And then we also see force B. And it's important to note that these forces are both being pulled at an angle. So it's pulling this housing unit right here. So the first thing I like to do with these problems is I want to consider what particular direction is this going, if any direction, and is this a balanced free body diagram? So for the free body diagram, we're going to be demonstrating the forces exerted on the housing unit, and because these two tow trucks are moving both in this direction, we can assume that there is an unbalanced force going up. So it is going, the unbalanced force, I'm going to label it with orange, unbalanced. And we don't know if this is important to the problem yet or not, but I just want to extract as much information as possible when I'm dissecting this. So we have an unbalanced force. And another thing that's important is that this housing unit isn't moving horizontally. So it's not moving in this direction or this direction. It's just moving up. So it's only moving in a vertical plane. It's staying completely still on the horizontal plane. And what that tells me is that on the horizontal plane, the forces are balanced. And when they're balanced, you can assume that force A on the horizontal is equal to force B on the horizontal. So to clear things up, I'm going to start with the free body diagram. Right here, I'm going to label the housing unit. Let me put it a little bit lower. I'm going to label the housing unit in blue, so with H. That's the housing unit. Now I'm going to put force A. This is A. And it's an angle of 48 degrees. And I'm going to put force B. And we can just label this as FA once again. And I'm going to put force B. Here's force B. And it is 32 degrees. So we have this, this simplified demonstration right here. And the best way I can think of simplifying this down even more is I want to break up these forces into their horizontal and vertical components. So what do I mean by that? I want to make this diagonal arrow into 2 triangles. I'm going to do that the same with force B. Alright, so now we have these triangles. And once again, remember that I mentioned that the horizontal forces are equal. So I'm going to circle it once again in a bright color right here. These two arrows should be equal. And we have these arrows actually demonstrated in this free body diagram right here. So this arrow right here should be equal to this arrow right here. And our reasoning for that is because this housing unit isn't accelerating in either horizontal direction. So it's not accelerating to the right, and it's not accelerating to the left. So these forces must be equal to each other, and they must be balanced. So I'm going to write an equation for that right now. So force A is known to be at 4,500 newtons. So Fa, 4,500 newtons. And we know this angle to be 48 degrees. So we can use some basic trigonometry to deduce a solution. So the sine of 32, so sine of 32 times FB should be equal to the angle right here. So FB sine 32, and then that should equal FA, and it is FA sine 48. And you might be asking, how do I know this? If we want to refresh our rules of trig, this right here is the angle, and then let me get a different color to label these. This is the opposite, and then this is the adjacent, and this is the hypotenuse. And remember, sine 48 must be equal to opposite over hypotenuse. So FA is the hypotenuse. And when you have the hypotenuse times the opposite over the hypotenuse, these two terms cancel out, just giving us the opposite. So this is the opposite right here. So it gives us what we want, the opposite. Let me get rid of that. So we have our equation derived right here. And we also have known values. So the rest of this just goes to plugging in those known values in order to solve for the opposite of FB, or the horizontal component of FB. So just to make it clear, I'm going to label this as the opposite of FB. And FA is known to be 4,500 newtons. And then sine 48 is also a known value, which should equal to FB sine 32. Apologize for the messy handwriting. So 4,500 times the sine of 48 is equal to 3,344. 3,300. And that's equal to FB sine 32. So if we want to solve for FB, the last step for us is just to divide 3,344 by the sine of 32. And then our ultimate answer should give us around 6,300 newtons. So that's our final answer. And if you want to find the magnitude of FA plus FB, you would just add the two values. And that's the basics of forces.